Welcome to the third lecture of algorithms and analysis. We'll be looking at the merge sort as an example of divide and conquer algorithm. And we'll be looking at two aspects of it, proof of correctness, using the same method that we spoke about earlier on. And then we look at trying to solve the algorithm using recurrence relations, and also another method, which is the tree method. So let's start off. And while I do have the poll everywhere, I would like to encourage people in the audience to actually speak up instead of just using poll everywhere, because that has some pluses and minuses. So I'm generally going to focus more on interaction in the auditorium. So just a quick review of the last lecture. We had the following two ways of defining either the big O or the big theta or the big omega notation. And this method, the first method, was sort of going forward. If you have a function f of n, and you want to see whether it is in the set of functions order of g of n, then this is the method using going forward. If there exists, the constant c and n naught, such that this condition is satisfied, then f of n is an element of that particular set. Oops, sorry. So f of n in that case is an element of that particular set, or as we'll just use the equal sign over here, which essentially means that the same thing, that f of n is equal to order of g of n, or f of n is an element of that particular set. The alternate method was going sort of in the reverse direction, where we're saying that we're focusing on O of g of n, or it could be any one of the other three notations, the big O, big theta, or big omega, and we're looking at it as a set of functions, right? And we're saying what is that set of functions, and then we're defining that whole set, okay? So it's two different, completely equivalent ways of looking at this, at the formal definition, and whichever you feel you're more comfortable with, you can use that, all right? But generally, we will be using the first notation in most of the course going forward. It's simply because it's a little easier, all right? So is there a chat session? So let me go back to the, somebody has a question on that. Maybe you didn't catch that. So the poll everywhere site, in case people didn't catch on to that, is as given. You can sort of try to note this down as well. That should hopefully make it easier next time. Right. And then we looked at the following theorem. I don't know how many of you saw that, because this was right at the end of the last lecture, where we said that, and this is Theorem 3.1 of CLRS, and it says for any two functions f of n and g of n, we have f of n is equal to big theta of g of n, if and only if f of n is big O of g of n and f of n is big omega of g of n. All right, and we saw this earlier on in the linear search example. We sort of informally introduced this, and we said, well, as you saw in the best case, the big O notation for the best case for linear search was big O of 1, O of n squared, and the omega notation, the lower bound, was omega of 1. And because both of these had 1 in common, so both omega of 1 and big O of 1 had the function g of n, which was 1. Hence, you could say that the linear search, the best case, is also theta of the big theta of 1. All right. Similarly, we saw for the worst case scenario that they had this particular function g of n being equal to n common for big O as well as big omega. All right. And when that happens, then you can assign the theta, the big theta notation, right? If that doesn't happen, then you can't really assign theta, because then you have an issue. So there'll be a lot of cases that we're looking at where this is the case. So this is the formal theorem, and So let's take a look at this theorem, and as you go forward, so let me also just make sure that you don't have any questions. So this is as far as we had gotten till in the last lecture, and if there's nothing, no questions there, we'll just move forward. So the first question is, how does one formally prove a theorem like this? All right, and proofs are an important part of this course. So you should be able to, take a theorem and to be able to prove it as and when necessary. It may not always be possible or within the scope of this course, but sometimes generally in the simpler cases, it should be possible for you to prove it, right? So any thoughts on that? How would one prove it? Is that completely intuitively obvious, or you don't have a clue? So I'd just like to get a feel from all of you that, are you familiar with such proofs? Have you done proofs like this in the past? So you can't really say because it's average, that's not a proof, right? So proof is very formal. For those of you who've taken more mathematical courses, you would know what a proof implies. And notice that it has something called if and only if. So somebody mentioned that you have to prove in both directions. That's completely correct. Okay. But how would one go about doing it? All right. So people are talking about some theorems. Perhaps not all of us are aware of that, and some of you have no idea. All right. So let's take a look at this, and this is a very simple case. And once you get a sort of handle of how you can conduct formal proofs, that'll become very handy for the rest of this course, because we will be talking about more difficult proofs perhaps as you go forward. Okay. But people do have some ideas I can see going if I look at this. So decompose and so on. So yeah, I think you have some ideas. So let's take a look at this. Now, let me share a secret with you. CLRS has a lot of solutions online. Okay, so for those of you who may not be aware of that, there are students like yourselves in the past, because CLRS is one of the most popular books that has been used for this course, this category of courses throughout most universities. And so there's a ton of actually worked out solutions on different websites. And I've actually taken the proof down, which is not there in the book. What I've done is simply taken it from this particular site, which is given over here. But if you just search online, you'll find there's a whole bunch of solutions available. And it's good for everybody to know, not just some of you to know, so that I don't want some of you to have an advantage. So everybody should be aware that there are solutions. And it's really useful if you want to just look at, there's a whole bunch of questions in the book. And if you just want to practice, you can take a look at those. You can try to look at the solutions if you don't have a clue, and try to, So sometimes that works, but don't always do that. You don't always reverse engineer. Try to initially solve a problem on your own. If you can't do that, look at the solutions, and sometimes the solutions will be there, sometimes they won't be there, right? So, for example, in the homework assignment that I gave, some of the solutions were actually online. Okay, so maybe some of you would be glad to know that. But don't make a habit that you're just going to look at the solution first, and because that's generally not a good way to make your brain work, right? You want to put in the effort to be able to solve a problem. Once you've done that and you have absolutely no way, then you could go to an LA or TA, and there's another way to as well. I'll talk about that in a minute. So let's take a look at the solution. It's reasonably straightforward. So first of all, we're breaking it down because it says if and only if. So the first part is, let's take a look at the left-hand side, okay, which says that f of n is equal to theta of g of n. And we need to, this sort of says that implies we have to prove that f of n is O of g of n and f of n is omega g of n, right? And the second part is the reverse, all right? So if these two are true, then that implies that f is theta of g of n, right? So how do we do that? Well, we'll take a look at it in two parts. So in the first part, we'll say, well, if f is theta of g of n, then we already know from the theorem itself, from the definition itself, the formal definition of theta, that there exists some n, there exists some n naught, and there exists some C1 and C2, such that this particular condition is satisfied for F and G. All right, so that just pops out from the actual formal definition. And then we say, well, if you look at the second part over here, if F is less than C2 G of n, then that sort of clearly implies that F is O, big O of G of n as well, because O of G of n simply says that there exists some C of G of n such that F of n is going to be smaller than that. All right. And so in that particular case, we have the C that we're going to use over here is simply C2. Okay. And similarly, if this portion is given to us, that there exists some C1G, which is less than or equal to F of n, that clearly implies that this condition, the condition for the big omega, will also be met. All right. And in that case, the C over here will be C1. Okay, so hopefully that should be clear. If just think about this and spend some time thinking about it, and it should be fairly clear to you. So that's the first part. The second part is slightly different, but more or less the same. Okay, so this is saying that if F is omega of G of n, then we know that there exists some n1 such that this is true. Okay, such that there exists some n1 and c1, and we take in specific values so that we can differentiate between the n and the c in the second in the later part. So we're saying that there exists some n1 and some c1 such that by the definition of omega, this comes out. Right? By definition of omega, we're saying that 0 is less than or equal to C1 G of n is less than or equal to F of n for some n1 and some C1. Okay. And similarly, if F of n is big O of G of n, similarly, there exists some other n2, okay, and some other C2 not to mix the two n1s, the two n's and the c's for the two cases. There exists some other n's and c's such that this particular condition is also true. Okay. Now, if both of these conditions are true, we can combine that and to be able to get the following statement. Okay, which is essentially what we're looking for if you want to have F being equal to big theta. Okay, because big theta has a lower bound on one side, and here we're getting the lower bound, and here we're getting the upper bound. So seems to be fairly straightforward. Yep. So any questions up to now? Do people agree with what's on the slide? Do you think there's a problem? And I would honestly recommend that people sort of, instead of writing everything down, sort of try to focus in on the actual lecture. Okay, just focus in, because, well, if it helps you in writing it down, that's fine. But if writing down all of these equations actually distracts you from actually understanding what we're talking about, then that's not really helping. Okay, so it might actually be better for you to just focus, and then you've got, the lectures are being recorded, so you can go back and try to re-listen, and the slides will be available, so you can, you don't necessarily have to write it down. It would be a lot more useful if you actually subsequently, if you really want to understand this material really well, then subsequently, let's say you have the copies of the slides, and then you take piece of paper, actual paper and pen, and try to reproduce the equations. Okay, so just take a look at the slide. This is what we're talking about. Now, you've got this over here. Can you do it on your own? Don't just say, well, yeah, it's kind of obvious. Don't do that. Well, can I actually use paper and pencil or paper and pen and actually prove it to myself? So just do that manually. Just working that out using paper and pen or similar is actually very useful. Okay, so I'm not going to repeat this over and over again, but just something for you to remember and perhaps you've been practicing this already. But that's been extremely useful for me when I was a student. So any questions on this slide? Is there any problem with this slide? Because sometimes, I make mistakes and there might be a problem with this slide. So think about it, and can you see any issue with this slide? Are you agreed with this proof? Okay, so part one, and part one was fairly straightforward. So let's just focus on part two. Are you agreed with this proof? Hint, there is a mistake. Okay, I want you to find out, I want you to look at this and tell me what could be a possible mistake in this, or maybe a slight flaw in the actual proof. So several hands, let's pick the gentleman in that row, in the gray shirt. Yeah. We're not saying that yet. You don't see that there, right? So you haven't said that. But that's exactly the point, right? Do other people follow? Somebody else had a similar comment? There were 3 people who had raised their hands, all right? So can you explain what you just said for the rest of the people? Yeah, so. Yeah. So very good. And can I get your name, please? Jack. So Jack's point is that we have 2 different values and we have 2 different conditions over here. We have N1 and N2. And this particular part says that for N greater than or equal to N1, okay, this condition holds. And for this second part, let's call it A and B. Okay, for A, we're saying that this condition holds for all values of N greater than N1, greater than or equal to N1. And for part B, it's saying that this condition holds for values greater than or equal to N2. Okay, but for omega, for theta, we need to have a single value. Okay, so we haven't actually specified, we've specified C1 and C2, but what about N? N is greater than or equal to what? So you could see that, some parts of this theorem were sort of not completely specified, okay? And you need to be able to specify, well, what is in fact N naught, all right? So for this part, what is N naught, all right? So as Jack mentioned, that N naught could actually be the maximum of N1, N2. Right, so we could just take the maximum of the 2 and essentially be looking for some value of N where this is true, because we're looking at asymptotic values, right? So we essentially want to say, well, as N becomes larger and larger, but how large does it have to be? What's the minimum value? So N naught is basically saying the minimum value. So essentially what we're saying is that we could simply say that N naught is the maximum of these, okay? So that's what I had left out over here, so that you could actually point it out. This sort of completes the proof. So hopefully everybody's okay with that. Right, so what's an alternative? I told you there is another method to find solutions. Any other thoughts on that? So here's another way to solve this, okay? All right, so for people who are actually familiar with ChatGPT, it's pretty powerful. It's quite amazing. I mean, I was quite surprised that when I put in this question, I wasn't really expecting a proof in ChatGPT, okay? But I actually solved it, okay? So look at this. I gave this equation. I put it down in terms of, big theta, because I couldn't find the Greek letter, and I used that, big omega, and so on. And so lo and behold, ChatGPT actually gave you the solution. So here's, another way. If you can't access the LAs and TAs, this is possibly a resource, okay? Although a lot of professors worldwide are now sort of warning their students, and here I am showing you how it's done. which is not exactly, I don't know if I should have been doing that, but I'm sure all of you guys are already smarter than a lot of the professors, and you know how these solutions are there, okay? And you might have even used it for solving some of your homework assignments. But be aware that it's only intelligence, right? So it doesn't always work. So can somebody tell me if it actually worked over here? Or does it have, can just take a look at it and see, did ChatGPT gave me the right solution? Or does it have some kind of a problem? It's kind of hard to read, but I'll just show you that in fact, it had the same problem that we just talked about. All right, so look at this. The first part seems to be okay. All right, take a look at it later on. The second part, so it did break it up into two parts and said if and only if, so it has to broke it up. So in the second part, the problem that it's saying is that it's C1, C2, and not, and it's sort of assuming the same issue that it's assuming that both of these earlier values, N1 and N2, were identical. Okay, so it made that mistake, and it assumed that N1 and N2 were the same, whereas in fact, both of these are independent C1s and N1s. Okay, so well, what did I do? So I said I chose ChatGPT, but in the second part of your proof, N naught does not have to be common between the two equations, F is equal to O and F is equal to big omega, right? And very interestingly, it actually corrected itself. Okay, so that's how useful it is. It's not just like a website, static website. It's actually so quote unquote thinking, right? So it apologized and said, well, a more accurate proof would be the following, and now it's used N1 and N2, and it's done exactly what we just spoke about. N has to be greater than or equal to maximum N1 and N2. All right, so pretty good. But so just be aware that you can't use this all the time in your homework assignments. A lot of times it just won't work. Okay, but this is just one example of how you could do it. Okay, so let's move on. So now proving correctness. This is an important part of this course. So this is a different way of thinking, and now we're going to look at how does one prove correctness of an algorithm. Okay, so let's say we have this particular algorithm, and this is the simple linear search. How does one prove this? Okay, and I've already given you a hint that we're going to use something called we can, right? Yes, we can. Okay, and don't just say very carefully. Okay, so we're going to use loop invariants. Okay. And has anybody come across loop invariants in any of the other courses so far yet? Loop invariants? Yes. Which course was that? Okay, 283. Very good. What about the rest of you guys? I'm sure the rest of you have also taken 283. Who else has taken 283? And you didn't raise your hands when I asked that question. Only Kyle was, awake in the class. All right. Okay. So let's take a look at loop invariants and try to ask ourselves a question that loop invariants are defined as follows. So you need to have a logical expression which has the following properties, right? So that particular logical expression must be true before the first iteration of some loop. Okay, so your code may have a bunch of loops. So you don't necessarily have to look at all the loops, but maybe there's some key loop which is at the heart of your algorithm, and you need to focus in on that particular loop. All right. So in this case, there's only one loop, right? So there's only one loop over here, which is while. And so if you've identified that particular loop, then you need to come up with a loop invariant, which says it's a logical expression which has to first of all hold true before the first iteration of the loop. Okay, and that's called the initialization. And then you've got the maintenance aspect, which says that if it is true before the iteration of any particular loop, then it has to remain true in the subsequent iteration. Okay, that's maintenance. All of this is simple mathematical induction, okay? And when the loop terminates, the invariant, okay? Well, first of all, you have to be able to show that the loop will terminate, okay? So the fact that the loop terminates is also an important component of the proof, okay? So the loop, you have to show that the loop will terminate, okay? And then if the loop terminates, then basically what we have to say is that it does give you some useful property, okay? And that useful property will be used in actually proving the correctness of the algorithm, all right? So initialization, maintenance, and termination. Those are three components of that logical expression that you have to think about, okay? So now, most of the times, it's not completely obvious what is the loop invariant, okay? Sometimes it could be fairly trivial, but it's not obvious at all, simply because, you know, perhaps you don't have enough training or enough examples that you've come across where you've come up with a loop invariant. So just think about it. And this may require a little bit of a thought as to what could be the loop invariant over here, right? So it's some logical expression which you should be able to show that it is true at the beginning before the loop starts, is maintained. In other words, if it was true in the last loop, then it's going to be true in the next iteration, and there has to be a termination component, okay? So, so let's see. Every element in the array at or before I is not the key. Okay, very good. So I don't know who came up with that. All right, Jane, is that? Yeah, okay, great. So, so very good. So let's listen to what Jane has just said, and I have that in my next. Okay, so at the start of each iteration of the while loop, the search key, I'm just rephrasing what just Jane said, the search key is not in the subarray A1 through I-1. So we're starting a loop, okay? So in this particular loop, you have the value I, okay? And what we're saying is that in the array A, for 1 through I-1, okay, before the value of I, the key is not in that subarray. Okay, so that's our sort of our hypothesis, and that's our loop invariant. And now we need to be able to see whether can we, so that's not complete. That's not the complete proof. Now we have to actually prove whether the initialization, the maintenance, and the termination, all three of those can in fact be proven. Okay. So let's go forward and see whether we can actually prove this. So let's take a look at initialization. So we've just said that the loop invariant is that the search key is not, so here I've repeated it, the search key is not in the subarray up till I-1. Is it true for at the time of initialization? Is it true at the time of initialization? When you initialize this loop, I is equal to 1, and so A sub 1 through 0, the search key does not exist in that. It's kind of trivially true simply because the array A0 doesn't really exist. Okay, so when things don't exist, the key can't exist in something, you know, that could be a philosophical question, but yeah, that's trivially true. Okay, that the key is not there at the time of initialization, and simply because A0 does not exist. Now, the trickier part, which is the maintenance. And in this particular case, it might be fairly straightforward to prove the maintenance, but I'm going to show you a methodology, my own perhaps a methodology, to be able to do it in a slightly more rigorous way, so that when things become more hairy and more complex, you don't get confused. Okay, but somebody in the audience, if somebody can give me a suggestion of, can you prove the maintenance? All right, so how can you prove the maintenance that if this condition is true up till A? So here you have A, all right, and let's say here you have I, some value, let's say 3, and we're basically saying that the key does not exist from 1 to 2, all right, then basically when I goes to in the next loop, it's not going to be true for the next part as well. So anybody would like to venture, how could you actually express that in so many words? Shouldn't be too difficult. It's almost obvious, but sometimes, when you're doing proofs, you have to state the obvious because, the professor doesn't know what's going on in your mind, or the TA or the LA. Okay, so how could you actually prove the maintenance part that it is going to be true? So essentially what we have to do is we have to make an assumption over here, and then we have to say, well, as I is incremented in, it's going to be true in the next loop as well. Yep. Anybody would like to give it a shot? Somebody, yeah.
So it looks like while first line you're checking
By the first line, what do you mean? Yeah, the line number 2. Okay, yeah.
And I guess when I go to the next step, I know
Yeah. But it's slightly tricky because you do have 2 conditions over here. All right, but let's look at it individually. So essentially what we're saying is that let's say that you got till the end, or you were somewhere in the middle, and if it was there in the previous iteration, then the loop would terminate. Okay, you'd go forward. You'd go down to line number 4. So you wouldn't go back into line number 2. And basically what we're saying is that if it iterates, then that condition has to be true. But if you're never going to actually go back to that loop, then that condition doesn't have to be true. Okay, so if this condition is true that you did find it, then you're not going to iterate. Okay, and you're going to go forward. All right, that's one part. Okay, the other part could be that you get to the end of the array itself. Okay, and if you've gotten to the end of the array, then clearly n is already I is already n plus 1, because I has to be greater than n to be able to exit or get to the end. Then in which case, basically what we're saying is that from 1 through n, it wasn't found. Okay, so yeah, you have the right idea. You just have to now express it. And so the method that I'm going to use maybe is a little, it seems a little complicated, but if you use this method, it's going to come in handy when you have more complex situations. Okay, so what I'm going to do is I'm not just going to use I, but I'm going to say, well, let's say that I has I'm going to allocate some other value. I'm going to say, well, let's say I is equal to k in the previous iteration. Okay, to differentiate between the current iteration. Okay, so I'm giving I a value of k in the previous iteration, because if I just said I has a value I in the previous iteration, now it's I plus 1, so it's kind of confusing. I mean, which value of I are you talking about? Are you talking about the pre-decrement value or the pre-increment value, the post-increment value, right? So it's easier if you actually allocate a temporary variable or another variable, and this will come in handy in a number of occasions in this course, that you actually allocate a different variable. Okay, so let's say that I is equal to k in the previous iteration. Okay, and so so in the current iteration, it has a value of k plus 1. So if I is equal to k in the previous iteration, okay, then just from the loop invariant, the loop invariant is saying that it was not in a1 through k minus 1. That is the loop invariant. Okay, so this is true. And now what do you have to prove, right? So I'm just going to use TST to show, which is an acronym for to show that. So we need to prove, in order to be able to prove this, we need to show that in the current iteration, where I is now equal to k plus 1, I has been incremented. by this statement over here, then the key is not is no longer in now A1 through K. Okay, so hopefully you can see the utility of this is that you initially say something, you say, well, what is already true, and then you say, what do we need to prove? Okay, so this is what we need to prove. If you put it in that way, it just becomes simpler. All right, so now once we've stated this, let's go forward. Now, this is the simple proof. We're saying that the while condition in the previous iteration ensured that A sub k is this particular part of it ensures that the key is not in the subarray A1 through K, because if it was there, then which would have naturally have to be in the kth element, in the kth index, this condition would have been true, and you would not have iterated the loop. Okay, you would have just gone forward. So the loop would have terminated. Okay, so hopefully the maintenance, I've gone through it in sort of more detail than perhaps I needed to, but I wanted to do that just to make sure that you can follow this, the thought process. Now, let's take a look at the termination. Okay, so the termination says that we need to have, first of all show that the loop terminates, all right, and then it gives some useful property. All right, so any thought on that? Can somebody, spell out what the termination? How can you show that the loop will in fact terminate? How can you prove that? Seems to be obvious, but just say it out. Yeah. Yeah. So if n is not infinity, then clearly the loop is going to terminate. Why is that? Because line number 3 is always executed, right? If line number 3 was conditionally executed, so let's say you had another subcondition which said if certain condition is true, then I'm going to increment I, then it would be trickier, okay? But since line number 3 is executed every time you iterate through the loop, then clearly I is going to be incremented every time. And assuming that n is not infinity, then clearly the loop is going to, at some point it's going to terminate, okay? Even if this particular condition is not true. So clearly it's going to terminate, and then once it terminates, do we have something useful to say? Can we, in fact, use some property at the time of termination to actually prove the fact that the linear search does in fact work? Okay, remember in the linear search, we're supposed to return a true if the key does exist in that array and a false if it doesn't, right? So can somebody, once again, tell me why does it actually work? Okay, based on our maintenance and based on the loop invariant, can we now just say that, yes, now we have a proof? Yeah, okay. Yeah. Yeah. So essentially what you're saying is that there are two possible ways of terminating this loop, right? One is that I went all the way till the end, in which case the value of I would be n plus 1, okay? And if I n plus 1, and then we clearly, the loop invariant is saying that key was not in I from 1 through n, then it wasn't found, okay? And in which case it's going to return a false, right? And let me just show that. So we've got the following cases. So we've already shown that because this is being run every time, so it's going to terminate, all right? And then we've got these two cases. The first case is if I is less than or equal to n, okay? Then somehow it terminated before I reached n plus 1. Then clearly from the loop invariant, it terminated not because of this condition, because I is less than or equal to n, it terminated because of this condition, right? If it terminated because of the second condition, then clearly we have found a sub I. We have found the key in I is equal to the value, all right? So previous value. So this condition would be true, all right? And if it terminated because of I reaching the end of the array, okay, if I is greater than n, then the loop terminated because due to this first condition, and in that case, clearly a 1 through n did not have the key, okay, and so you're returning false, okay? So it's fairly simple case of using a loop invariant to actually prove that an algorithm actually works. But what you'll see is as we go forward, this becomes extremely useful. Okay, and in practical life, the question is how often does the industry actually use loop invariants? It's a good academic exercise, and perhaps if you were working at Google and you had 1,000 lines of code, you may not be using loop invariants to prove the algorithm, and hopefully in which case you wouldn't have the scenarios where you're giving a big convention and suddenly you get the blue screen of death and something went wrong with the algorithm. In practical cases where you have very large algorithms, it's kind of hard, right? But it's a good academic exercise. Okay, so one must know this technique, and if you really had to prove something in a big algorithm, perhaps you may be able to do that. And if you're a professor or an academic, sometimes it becomes very useful to be able to do that and write papers. Yeah. So let's go forward. So now we've seen the proof, and we've seen loop invariants, and now let's try to look at some more bigger algorithms and slightly non-trivial algorithms. All right. So as I mentioned, that the next major topic in this course is designing algorithms. So we've sort of looked at how you could create an algorithm. You've looked at how, if you had an algorithm, how would you analyze it? How would you prove its correctness? And now the next question, the major topic, will be, and of course, this is just the beginning of the course, so we'll go into all of these subtopics in more detail, but I'm sort of giving you a big overview of the course, and we're giving you some small examples of each one of these cases. So now we're going to look at how does one actually design an algorithm, okay? And there are a number of techniques which are used to design algorithms, and you might have come across some of these. For example, greedy algorithms are some of those which are used quite often. Randomization and dynamic programming, you probably haven't. Has anybody come across either one of those two design paradigms? Dynamic programming, anybody? Okay, which course is that? Just on your own? But was there any course at UNC that you've come across, dynamic programming or randomization? Yeah. Yeah, and so I guess none of you have actually taken those optimization courses. Safe to say. Yeah, sorry. Some people might have taken it. Okay. Okay. So it might be a good review, and we will get to those design paradigms somewhat towards the end of the course. Okay. But let's start with divide and conquer. Okay. So divide and conquer. It's a good political philosophy as well, as you might be aware. A lot of nations have used this to be able to take your opponents and to divide them up and to break them up and then to be able to conquer them. But in computer science, it's slightly more theoretical, slightly more detailed as well. You're not just going to take your opponents and divide them up into two groups and then get them to fight against each other and conquer them, but you're going to actually do a recursion as well. So this is not just going to work with two major groups. You're going to say, well, I've divided the major groups. Now I'm going to divide the small groups again and again and again until I get, perhaps one person. That person can't be an opponent of himself or herself, and so it's going to be a recursive structure. Okay. So how do we do it? So first of all, it comprises of three parts. Okay. So it's not just divide and conquer. It's actually divide and conquer and combine. Okay, but that becomes a mouthful, so I guess people just stick with divide and conquer. Okay, So we're going to divide the problem into subproblems, and those problems have to have two components, two aspects. So they have to be similar to the original problem. Okay. If you divided the problem into two smaller problems which are not similar to the original problem, then it's not divide and conquer. Okay. Can somebody give me an example of maybe a real life situation where you're doing divide and conquer? You think you're doing divide and conquer, but it wouldn't fit into this definition. That, in other words, it's not similar to the original problem. You can think of a real world example where one does do divide and conquer. Any thoughts? A real world example where you have a problem, you break it up into smaller problems, but those smaller problems are actually not similar. They're not just smaller versions of the bigger problem. Yeah, Jack. Yeah, exactly. So, if you are leading one of the student groups, then you might be the vice president of that group, and you say, well, we've got to run a project, and I'm going to have 5 people reporting to me. So the first person is going to work on one component of the project. Another person is going to work on marketing. Third person is going to work on finance, and so on. But though that has, you've divided the problem into smaller problems, but those are not similar or smaller versions of the bigger problem. Okay, so those won't be called, that technique won't be called divide and conquer. Okay, it has to be similar to the original problem. And secondly, it naturally has to be a smaller version of the original problem, right? Because if it's not smaller, then what's the whole objective? If it's the same size, then you're wasting your time. Okay. Secondly, of course, the second part is kind of obvious. You have to individually solve the smaller subproblems. You have to conquer them. Okay. And you're going to use recursion, right? So you've taken a big problem, divide up into 2 smaller problems, let's say, or 10 smaller problems. And now you're going to make each one of those smaller problems, unless it becomes of a very small, trivial nature, you're going to try to keep on dividing those up into smaller and smaller subproblems, okay, until you get to the most trivial scenario, okay? And once you've divided and conquered each one of the smaller problems at that level, so let's say you are the CEO of the company, you've just broken up the problem into 2 smaller parts. Now, the 2 people who are reporting to you have solved the smaller problems. Now, you have to combine those. Okay, so at that level, at each level, you have to do all 3 of these. Okay, so you've also got to do the combination, which is an extremely important part. Okay, so it's not always obvious. Let's say you've divided up a problem into 2 smaller problems, but then you don't know how to combine it. Okay, so that could be a problem. So you have to be able to know how to combine it. And a lot of times, this is actually the more challenging component. Okay, well, all 3 of them are somewhat challenging, but this is sometimes more challenging as you go forward. Okay. So let's take a look of an example of a sorting algorithm, which is called merge sort. Okay, how many of you have come across merge sort before? Almost everyone. Okay, everybody's taken 210. Well, sometimes we don't cover it in 210, but yeah. So merge sort is the following. It says, well, in all sorting algorithms, let's say that you have n elements, okay, and you have to sort it into a non-decreasing order. Okay, increasing order, but non-decreasing means that the 2 elements could be the same as well. Yeah. And so what we're going to do is we're going to divide naturally into n upon 2. So it could be divided by 2, although that doesn't necessarily have to be the case. You could divide it up into m sequences, m smaller subsets, but let's assume the simple case that in merge sort, normally you divide by 2. Okay, so you've divided up into 2 sequences, each one of them approximately half, because if it's an odd number, n is an odd number, then they might be slightly unequal, right? And then you're going to conquer the 2. Okay, so you need to be able to recursively. And that's very straightforward because you just need to do a recursion, right? You're going to just call yourself and you're going to say, I'm going to recursively sort. And the tricky part is to be able to combine. So you've broken it up into 2 smaller problems, but now how do you combine it? Okay, not completely obvious. So let's take a look at the way merge sort works. Okay, so let's say you have the following original sequence comprised of a bunch of integers, 18, 26, and so on. You can clearly see this is not sorted. Okay, so what we're doing is we are initially breaking it up into two parts. So we've broken it up into two because this is number has 8. So it's easy to break it up into two parts, which are each 4. So notice that we're not really sorting at this time. Okay. At this stage, we're going to break it up. We're going to divide. We're going to somehow conquer these. And when they're going to come back to us, these individually are going to be assumed to be sorted. Okay. How is that going to be done? Is going to be done when we're going to call ourselves recursively. Okay. So now we're going to recursively call ourselves. So we're going to say, well, we need to merge sort again. It's 4, so we're going to break it up into 2s. And eventually you're going to see that you have the sequence just has individual numbers. Okay. Now, individual numbers obviously don't need to be sorted. They're already pre-sorted. So now when you are at this particular stage, you now need to be able to figure out how you're going to actually merge the two. All right. So let's say you're at this particular stage and you have 18 and 26. Okay. Now you need to be able to figure out how you're actually going to sort or combine these two so that these two remain sorted if they're not. So kind of obvious. Okay. Well, in this particular case, it's kind of obvious. You'll say, well, let's take a look at each one of these two numbers. We just have two numbers and look at 18 and 26. Whichever is smaller, we're going to put that first. We're going to put that first. Okay. So in this case, 18 is smaller, so nothing changes. But in this particular case, 6 is smaller than 32. So we're going to interchange them. And so you can see that at this particular stage, it was fairly straightforward to be able to combine. Okay. As you go forward, it's not kind of obvious, but you can see that it's still easier. Okay, simply because now you have two lists or sequences which themselves are individually sorted. So it's relatively easily. Essentially what you could do is you could look at, let's say, the first of these two. Okay, you could say 18 and 6. Well, you just need to compare 18 with 6. You don't have to look at the rest of the numbers, and you say, well, which of these is smaller? So 6 is smaller, so we're going to put 6 over here. Okay, and so we're going to cross out 6. Okay, it's already done. Next, we're going to look at 32, and we're still going to look at 18 because 18 is not yet done. Okay, so we're going to compare 18 and 32, which is smaller. Well, in this case, 18 is smaller, so we're going to cross out 18. All right, now what's left is 26 and 32. 26 is smaller, so we're going to put that in. We're going to cross it out, and then 32 is the last one which is left, and we're going to put it in. So that's how we sort of combined two separate sequences, which themselves are individually sorted into a master list, which is master sequence, which is sorted. Okay, but you could have seen, you could have guessed that this is a little easier than if these two were completely unsorted, it would have been more difficult. Okay, the amount of comparisons would have been more. Okay, in this case, we just had to compare the two smallest numbers on both of these sequences. Okay, so I'm not going to go through this, but you can see you get the idea, and this should hopefully be a refresher for all of you. So now that we've figured out the sequence, let's take a look at the actual code. Okay, pseudocode. So this is the first part, which is doing the division, the dividing, and the conquering. Okay, and then it's going to do the merging part. So the first part is, how do we divide up the problem? Well, fairly straightforward. We simply divide it up into two roughly equal parts. We said Q is equal to P plus R divided by 2. So let's assume over here that we have an array which has a value of n. In this case, we have the parameters are P and R, the arguments are P and R. So let's say that we call it with the values 1 and n. N in this case being 8. So P is 1 and R has value of 8. And so P plus R is 8 plus 1, 9 divided by 2. So we get Q, which is the the lower value of the two, and you get the following merge sort A14, and you have merge sort A58. Okay, so that we've simply divided up into a recursion on calling itself with smaller numbers. So you can see that the problem is exactly the same, and it is smaller. So it's satisfied the first condition. And we're calling it twice. So we're basically doing a recursion, but we're doing a double recursion, right? And in the second part, we're calling the second sequence, okay, from Q plus 1. So now we've done the initial parts, and then finally we need to do a combination. So now we need to find we need to write a separate algorithm for doing the combination. And when we combine these two, we're going to give it one more parameter, right? Because we clearly need to know where was that actual division made, right? So we're going to give it P and R. So P is there and R is there. But in addition, we have to give it Q, because Q was where the actual boundary was made between the two sequences, the two small sequences, okay? And what this is going to do is going to basically take both of these separate sequences and it's going to merge them. So let's take a look at how the merge procedure would work. So this is all there in CLRS. Sometimes I use version third edition, and sometimes I use the fourth edition. So, you know, there's some small improvements sometimes made in the fourth edition of CLRS, and those are useful. But sometimes it's just easier to work with the third edition. So you might want to, you know, have both of those, and you don't necessarily need to refer to CLRS, but it does help if you look at the book once in a while. All right. So here's the merge sort, the merge procedure, or the merge pseudocode. And let's say we're calling it with the following parameters. We're calling it with the following arguments: A, 1, 4, and 8. That's simply because we have the two sequences that we need to merge together, 6, 8, 12, 6, 32. And now notice that I'm assuming that these subarrays were somehow already sorted out. Okay. So I'm assuming that when I did the recursion, the lower, the previous, when I got merge sort done, when I got each of these done, they actually took these arrays as inputs, and they gave me the sorted versions of that. And it's all sorted within A, but they are separate. So the first 4 elements of A are sorted, and the next 4 elements of A are sorted, but they're not globally sorted inside the array. Okay, so now we need to be able to write a pseudocode to be able to globally sort the array, right? So what we need to do is we're going to the output of this merge sequence is going to be the array A itself. Okay, and so naturally you can think that, well, if the output is going to be inside the same array, we clearly need to have some temporary arrays where we're going to put in, we're going to put in some initial values, maybe copy these, and then the sorted versions are going to be copied back into the original array. Okay, so we're going to make copies of these smaller sequences, and then we're going to sort them, and as we're sorting them out, we're going to put it into the main array, which is going to be returned by the algorithm. Okay, so let's take a look at how this works. So as I mentioned, that initially you've got to take these arrays, and I'm going to have 2 smaller arrays, left and right, L and R, which are simply going to be copies of the left and right parts of the big array. And to be able to do that, we need to have a size of how big the array was. So clearly N1. So L is going to be of size, let's say 4. And J and R is also has to be of size 4. Now these two happen to be the same, but they don't necessarily have to be. So how are we going to calculate these 2 variables, N1 and N2, which give you the size of L and R? Okay, well, you should be able to see that is going to simply be able to manipulate P, Q, and R. Okay. So in this particular case, you're simply going to say, well, 4 minus 1 plus 1, 1 is the initial value of P. And in this case, you're basically saying 8 minus 5 plus 1, which is the value of N2. Okay, so N2 is 4 and N1 is 4. Okay, so those are now the sizes of the L and the R arrays, which are temporary arrays. All right, now notice that I also have actually an additional element, which is sort of a dummy element. So it is an N plus 1 element inside the L and R arrays. It comes in handy sometimes to do that. And we're going to initialize those to have infinite values. Well, some of you might say, well, how are we going to get infinity if you actually write this code? Any ideas how do you actually define infinity inside a real code in Java? Yeah. So if it's a long, or if it's a short, or if it's an integer, there's a way to get that, and you just use the largest value. And actually, Java actually gives you that. Okay, you can get the largest value, and you just put that into this particular field. Okay, corresponding to the actual variable being used. Okay, depending on the data type. So you define the infinite values. Now that's going to come in handy as we go forward. So as you can see, we've done with this part, which is simply doing the copying. This part was simply calculating the sizes of the small arrays. This portion is simply copying the array A into L and R. And this is initializing these dummy variables, which are sometimes called sentinels, in these particular locations, okay, into the N1 plus first element of L and R. And then we start our actual merge procedure. We start with initializing two variables, I, J, and we're going to use K. And these are individually going to traverse those particular arrays. So I is going to traverse L, R is going to traverse J, and K is going to traverse the main array K. Okay, so we obviously start with I is equal to 1, J is equal to 1. We start by K going from P to R, because R is now the maximum value of the original array. Okay. Now, if you go back and just think about what we actually did, essentially what we did was we compared these two values, and we said which one is smaller, and whichever was smaller, we put it over here, and then we crossed it out. Okay, so we said that, well, we're going to compare 1 and 6. If one is smaller, we're just going to copy it over here, and we're going to remove that. Okay, so that sort of says that we're going to increment J to be 2. Okay, so we're going to say, well, is L smaller, L sub I smaller, or R sub I, or R sub J smaller, and whichever is smaller, we're going to copy that, and we're going to increment that corresponding variable which is going through that index. Okay, fairly straightforward. Hopefully, up to so far, you can see how that is now. If you are able to go through this whole algorithm, you should be able to get a sorted version. Why do we have these infinite values, these large values? That comes in handy at the end. Okay, so you should be able to figure that out. So now let's take a look at the correctness of merge. Okay, just the merge portion. And first question is, what would be the loop invariant? So let's assume that we're going to be using loop invariants for this. And the question is, what should be the loop invariance for merge? Okay. A little tricky, perhaps, more tricky than linear search, but maybe not that difficult, simply because we've sort of, if you just think about what we're basically saying is that, now the first question, where is that loop that we're talking about? Right, so it could be one of these loops, but clearly those loops aren't really doing anything very useful. So you need to identify which loop are we going to focus in on. Okay, so clearly it seems to be this particular loop, which is at the heart of this equation, of this algorithm. And if we can prove something useful at the termination of this loop using a loop invariant, then that could come in handy. Okay, so let's take a look at this loop and see if can somebody come up with a concise, relatively concise statement, which could be the loop invariant. Okay, it's a logical expression which says that, which is true at the beginning of the loop, which can be proven to be maintained, and which at the end tells us something useful. Yes. So say that again, I'm sorry. Of the sub-array. So now we have two sub-arrays over here. Okay, so we have L and R, and we have the main array where we're putting back the sorted stuff. So are you talking about L and R, or are you talking about A? First, let's identify that so I'm not confused about what you're saying. So you said sub-array, and you said the portion of the sub-array is sorted. So think through that, and if somebody else would like to help. Yeah, sorry, I need to look all over.
By the time and we know that they have our I value, J value, are the lowest value.
Okay, so I'm sorry, I forgot your name. Connor. Okay, so what Connor's suggestion is that you look at I and J values, and let's say I is over here and J is over here. All right, and you're basically saying that the loop invariant could be the logical expression, which basically says that everything in L, perhaps either including or excluding I, is sorted, and everything including up to and including perhaps J is sorted in the sub, which is sort of in line with what the lady over here. You're not Jane, are you? I get confused sometimes. What's your name? Sorry. T. Okay, so sort of in line with what perhaps T was originally thinking is that you're focusing on the sub arrays, all right? But remember, you need to get something useful out of it, and I already gave you a hint that the output is going to be in the A array, which is the original A array. Okay, we've made these temporary copies, and now a major flaw in your thought process is that, as I said earlier over here, we're already assuming that these subarrays have already been sorted by the divide and conquer component, right? So we're now in the combined portion. So it wouldn't be very useful for us to say that, well, the L and R are sorted on their own. That's already given. So now we need to say something useful about what? I don't see your hand, just shout out. Yeah. Yeah, yeah. So what's your loop invariant? What's your logical expression? So let's say K is over here. So let's say K happens to be at this particular point, right? What can you give me a logical expression that would be true or that would help us? Yeah, so this is R. Yeah. So, but that itself is not really giving us enough ammunition to be able to prove something useful. Yes. Okay, so that is now making something. Can I get your name? David. So David's suggestion is sort of giving us something more useful. Basically, what David is saying is that if, let's say, K, at some point where you have K, wherever you have K, you can somehow say that everything before K, maybe, or including K, is sorted. Okay, so that would be something very useful, because as you're going from K is P to R, all right? So eventually, as K gets to R, you're sort of saying that everything before that is now already sorted. So that's one part. of the loop invariant, I need to have some more parts to it. So you've said something very useful about K, but we need to say something useful about I and J, because now this is more complex. There's not just one variable, there are three variables involved. So we need to say something useful about all three of those. So let's say I is over here and J is over here and K here. So you've said something useful about K. Now, can you restate what you were saying about, let's say, I? Yeah, so you're sort of getting there. Basically, what we want to say is that this stuff has actually been crossed out. Okay, remember we're crossing it out. We're putting it in.